Welcome everybody in the lecture hall on Zoom from the future. Today we are going to look into tolerant retrieval, not information retrieval, that's the whole course, tolerant retrieval, which basically means it's the did you mean feature that you see on search engine, right? You type something, there is a typo, and somehow it still figures out what you're looking for. But before we start this, I have a few questions for you, actually quite a lot of questions that I'd like you to answer before we start, just to refresh things. So here we go. Here's the first one. What documents does the query A and B return? So this is the standard inverted index, right? The usual structure. And these are the possibilities. I have 4 different lists, which are ordered lists of document IDs, but as you know, the order doesn't matter. It's just I put them that way. It's just set semantics. So what documents does the query A and B return? So you remember that we have this boolean query language with and, or, and not, and we now know how to execute all of these queries. We even know how to optimize, because you can do it in any order, but there are ways that you can accelerate things a little bit. Now the sun is paying us a visit. Let me think. So we have 40 answers so far. Let's see if there is a trend. Well, we have a majority, 97% of you, who think it's 3 and 8. So is it 3 and 8? Well, you have to compute the intersection, right? 8 is the intersection. So you have 1, 2, 3, 5, 6, 8 for A, and you have 3, 4, 7, 8, 9 for B. And so the only 2 that are in both is 3 and 8. Why not 5? 5 is also on both lines, right? Why is not 5 part of the results? It appears both in the line of A and B, right? Yes? Yes, the first number is just the counts. This is called the document frequency. So this 5 that you see in purple after the B, that's not an actual document ID. That is the total number of documents, and you can count them. 1, 2, 3, 4, 5. So 3, 4, 7, 8, 9. That's 5 of them. That's the 5. Yep, excellent. Okay. Let's close this one. Now, we looked into phrase queries. It's a different language, so it's not about Boolean queries. It's about entering a phrase, typically in quotes, and it's looking for a match. But now it's order sensitive, right? A phrase has an order in the words. So we saw that we had false positives if we were using byword indices. So you remember that byword indices is a modification of a standard inverted index, in which instead of having single terms, you have pairs of terms, right? Then you have a posting in there if these 2 terms appear exactly one after the other in the original document, right? So of course, set semantics is not enough. You have list semantics for that, list of words. And so we saw that there are false positives there. You return too many documents. If all you do is take the query, which might have, let's say, 10 words, and then you do a sliding window of 2 words over the query, and you look for the documents that have each one of the pairs that you have in your query, right? But we have false positives. How do we decrease them? Do we use byword indices? Do we use phrase indices with bigger tuples of words? Do we post-filter the results, but you still might have some false negatives? Or do you use phrase indices with smaller tuples of words? I think the first answer is a bit silly, because we started with a byword index. So if you just keep using it, that's not going to reduce anything. But anyway, let's see. So there is a majority here. And yes, you are correct. Indeed, you need larger tuples. So by word is only one way. There's also 3-word, 4-word, 5-word indices. You just make the window of word a bit larger. And the larger the window of words, the less false positives you are going to have, because you're getting stricter and stricter in what you want to see in the documents. It's never going to be perfect, but of course, if you increase the number of words, the size of the tuples, at some point, it kind of gets very accurate, right? Okay, so by word, 3-word, 4-word, and so on and so on, K-word indices in general. It's important because today we'll see other kinds of similar indices, but not based on the number of words, based on the number of letters in the words. So we'll look at them. These are called K-gram indices, but the principle is the same. It's just letters instead of words. All right. Now, what documents does the query C or D return? Now, this should get easier every time because now you're getting quite familiar with the index structure. The answers. We arrive at 40. And we have a majority answer with 1, 2, 3, 4, 5, 7, 8, 9. No, there is no 6, right? So the difference between the first two is there is no 6, basically. So let's look at C or D. So we have 1 in both, 2, 3, 4, 5. There is no 6, right? So this is the reason why the second answer is not correct. There is no 6 anywhere in here, right? So this is why it's the first one, 1, 2, 3, 4, 5, 7, 8, 9. All right, so you have a good understanding now. Let's do more complicated. What document does the query D and not E return? D and not E. So here it's more of a mental gymnastic. Somehow our brain is not wired to compute not efficiently. This is something that takes an additional cognitive effort in order to implement the ends. Just an or just an and is relatively easy, but a not. Yeah, 1589 because the 3 goes away because it's here, right? Of course, when I'm saying the brain is not wired for that, I'm not saying it's not easy, right? Because everybody answered, but the pathways in the neurons are actually longer. It takes more energy. All right. Have yet another one. Plenty of questions today. Which of the following is not an encoding? Unicode, ASCII, UTF-8, macOS Roman. All right. Interesting. Is the majority correct? In that case, actually not. It's Unicode. Can anybody tell us why Unicode is not an encoding? We can throw the microphone at you. Of course, you can answer on Zoom too. We have the Zoom chat. Why is Unicode not an encoding? On Zoom, maybe? Anybody on Zoom knows why Unicode is not an encoding? I see.
Unicode is just a character set.
Yes, exactly. It's a character set. What is a character set? It's just a catalog, right? You have a list of characters, a very large list, of course. There's millions of characters. And each character has a number. There's character number 1, character number 2, character number 3. Of course, we're computer scientists, so we like to put that in base 16, right? But it's still a catalog. That's nothing else than that. The actual encoding is what maps these numbers to bits, right? But there's more than one way of doing that. UTF-8 is one of the way, this elastic way, but there's also UTF-16, UTF-32. So UTF-32 would basically be a fixed length encoding. UTF-32 is basically encoding every character on 32 bits, which is of course very expensive, but there's no elasticity, right? You just put the 32-bit integer of every character. For whom is that clear? All right, so Unicode is a character set. UTF is an encoding that works with Unicodes. All right, the others, they are all encodings. ASCII, UTF-8, macOS Roman. There's a very long list, actually. If you open text files and select an encoding, there's a very long list of that. But UTF-8 is really the recommendation. Okay, let's push you a bit more now. What documents does the query A or B and E and F or not G return? You might observe that it is in conjunctive normal form, right? On the top level, it just end, and then you have nested variables or ors. So let's look at your first answers. There is a majority with 2 and 4. So let's try to be smart here, because I showed you a technique, right? So when you have plenty of n's, you need to look at the size of every one of these posting lists. How many of them? 3 here, right? There's A or B, then there's E, and then there's F or not G. Of course, if you want to know the size, for E, it's easy. E has 4 documents, so that we know. There's 4 of them. A or B, you don't have to compute an exact value. You can estimate it. Just sum over A plus B, like the number in A plus the number in B. So it's 6 and 5, the purple ones, right? So that's 11. So there's 11 at most. Then there's 4. And the third term, F or not G, you can estimate it with 6 plus the complement of 4. Since there are 9, that's 6 plus 5, that's 11, right? So basically what you learn here is that the first term A or B can be long, E is rather short, there's only 4, and then F or not G is longer. So it's probably a good idea to start with E, because that's the shortest one, right? So you can already say, just because it ends everywhere, that whatever we return will anyway be a subset of 2, 3, 4, 7, right? So you can already start from there, and then you can eliminate things, right? So for example, you could look with A or B, because that's the easy one. There is no not, since there are ties. 2 is in A, right? For now, we keep it. 3, it's in B, so we keep it. 4 is in B, so we keep it. And 7 is in B, so we keep it. Okay, that didn't really help us, right? So, but at least we didn't eliminate anything, right? So A or B and E is the same as E, basically. It's still 2, 3, 4, 7. Okay, so now let's go to F or not G. So it needs to be in F or it needs to not be in G, right? So 2 is in F. We keep it. 3 is not in F. Okay, so let's look at G then. It is in G, right? So it's not in F and it is in G. So it checks all the boxes to be eliminated, right? So F or not G for document 3 is just not true. So 3 we throw away. Then we have 4. 4 is in F, so that's fine, we keep it. 7 is not in F, but it's in G. So we throw it away as well, right? Because it's neither in F nor not in G. For whom is that clear? This is how we have 2 and 4 left, right? So again, it's important, you should really not compute everything by hand, right? If you start computing A or B and then F or not G and so on, it's complicated, right? You really have to do it in a more optimized way. All right. So the correct answer is indeed where the majority is. And then I'll stop with that one, and then we start with the lecture. We saw last week index and query expansion. How do they relate with space and time? Right. So is index expansion taking more space, but the queries are faster, or is it taking less space and queries are faster? Is query expansion taking less space, but queries are slower, or is query expansion taking less space and queries are faster? Answers. Remember that query and index expansion are the two ways of, it's the asymmetric way of expanding queries and indices, right? The symmetric way is with equivalence classes, just puts the terms into bags, sorry, the words into bags, and then put them together in the index. But we saw that there is an asymmetric way that wouldn't be an equivalence class, that just you trigger expansions, right? If you have a word, then you add other words and so on and so on. And we saw that you can either do it in the index by expanding the index and by adding more document IDs by transitivity, or you can do it in the query, leaving the index untouched. It's equivalence, right? But these are the two ways of doing that. So you are correct that indeed the index expansion takes more space, right? Because you expand the postings list, but the queries are faster because it's a direct lookup, right? The query expansion takes less space because the index stays as it is. So this is why less space, but queries are slower because you expand the query. So that's something you do at runtime, right? Expanding the index is at compile time. Expanding the query is at runtime. This is why the queries are slower if you do it at runtime. This is true, by the way, not only of information retrieval, it's everywhere, right? What you do at compile time is something you save from the runtime. By the way, a trick, if you interview for a company and they ask you to compute something, and then how do you accelerate that? Then very often the extreme way of accelerating things is to pre-compute all the combinations. It's theoretical, but technically you could do it and then end up with an O of 1 at runtime. All right. Okay, so let's stop here. And now go back to the slides. Okay, are you ready? Let's start? Okay, let's go ahead then. So what we've seen so far is, recap, that we are looking at collections of documents that we want to look information in. So we have an input set of documents and we have a query that was in the boolean query language in the first week. And we want to output a subset of the documents of the collection without any order, without any ranking, and so on and so on, just a subset, right? we saw that in order to do this, the efficient way is to build a standard inverted index where it's called inverted because you have the terms and not the documents on the rows. And every term is associated with the list of all the documents that contain it, right? Every little square in blue is called a posting, and a posting is actually a pair made of a document and a term. It's a pair, but we only display the document ID because the term is taken from the left every time, right? So this is why, for example, we don't say A1, A2, A3, A5, right? Because A is just on the left. So this is why we just write 1. But the little square on the top left with 1 actually means A1. That's a posting. All right, so that's the standard inverted index. Then we saw that preparing that index requires many steps in the inputs documents. We need to tokenize, we need to do a lot of processing because it's not trivial at all. We even saw that depending on the language that you're looking at, it might actually look different. So this is what we saw last week, and now we take it as granted. Of course, it shouldn't be taken as granted, but now we move on from this today, right? But hopefully now you understand that this is quite complex to do, right? We saw that there are stop words, especially at times where we didn't have the resources we have today. So we threw a lot of the entries in the standard inverted index that have words that are very frequent. So in the standard inverted index, stop words would basically correspond to a very, 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 very long postings list, right? Basically all the documents in the collection, and that's not very efficient. So this is why we throw them away, but the trend is to no longer do that so much because we have the resources. All right, then we saw that we can group together the tokens that are from the same family. We put them in the same group. This is called the type, right? And the type is then put as a term in the standard inverted index. So again, token, word, term, type. You need to understand the difference, right? A token is when you look at the input document, that's the actual characters that appear in the documents. A type is an equivalence class like this. Term is what is on the left here in the standard inverted index in yellow. These are the terms, right? So term is used for an entry in the standard inverted index. And word is used a bit casually. I mean, when people say words, it depends on the context, right? So this is why I tend to use it like set of words, list of words, bag of words in this context here. But depending on the context, when people say word, they might mean a token, they might mean a non-positional token in the sense that it's a token, but you don't know where it is. You might use it for term. So yeah, that's how I feel it is used. But the word term, the word token, these have a precise meaning, right? And for token, you have to distinguish between the notion of a positional token and a non-positional token, right? A positional token is a token, you know exactly where it is in the document, specific position. A non-positional token is you forget the position. It's just the list of characters that it's made of. All right, for whom is that clear? All right. Okay, then as part of the linguistic preprocessing, we saw that we can use stemming or lemmatization depending on the language, but in English, stemming works actually quite well, and the Porter stemmer is quite popular in order to build these equivalence classes that I told you about, right? So again, the goal of this stemmer is to build these things, right? You basically stem the words and that gives you the equivalence classes based on what you obtain on the right. Of course, what you get on the right doesn't mean anything. It's a purely algorithmic way. And if two tokens give you exactly the same stemmed roots on the right, then you just put them in the same packets, in the same equivalence class. Okay, then we looked into an optimization technique in order to deal with the case that you're merging a very long and a very short postings list, right? So in that case, you have the skip pointers that help you accelerate things a little bit. And in practice, we like to take the square root of the length of the posting list. So that would be the purple number. You take the square root of that, and you basically put the skip pointer. So in that case, it's 4 pointers that skip 4 every time. You could do 5 times 5, 6 times 6, and so on and so on. Right. So this is how you skip things. It's a good idea to make sure that you go in the book. There is the algorithm for posting this and skip pointers. And sometimes in the exam, there are questions that ask you like, how many comparisons do you do, right? And so for this, we use exactly the algorithm that is shown in the book, right? So we basically give you 2 postings lists and we ask you how many comparisons do you do with or without the skip pointers. Okay, now the byword indices, it's for phrase search, right? So this is when you have a sentence in the query. So in search engines, typically you can add quotes in order to force a phrase search. One way to do it is byword indices, where you index over the sliding windows of 2 terms. We also look at a second kind of index that is a positional index that is also an extension of the standard inverted index, but in the postings lists, you don't just have the document IDs, you also have all of the positions that the term appears in. For example, 2, the 4th row here, 2 appears in document C 3 times at offset 4, at offset 7, and at offset 11, right? Offset in terms of words. So it's the 4th word, the 7th word, and the 11th word. So of course here, it's list of word semantics, right? Because you know exactly, you could actually reconstruct the original documents up to the stemming and lemmatization, right? You couldn't get rid of the equivalence classes if you had the equivalence classes, so that you couldn't reconstruct, but at least you could reconstruct the order of the words. Okay. So this is called the positional index. And in that case, these little numbers here, this is what you call a positional token. Positional token, because every time you have specific position in the document, right? Okay, now let's move on. What I have not told you about is how, when we look up, when there is a query and we look up specific words or specific terms, how do we search the index? Until now, I just told you there is just this list of terms and that's it, right? But there are actually data structures for this, and the good news is that you learned them in the algorithms and data structure lectures. So that should be a bit of a refresher, but this is pretty much what we will use today. So here's an example of a standard inverted index. Looks a bit different in the display, but it's just the same, right? With the document frequencies in purple, and then the postings list after that. So how do we look up terms based on a query if I give you that? For example, the first question you ask is, does it exist? So now I'm going to give you a word and I ask, does it exist or does it not exist, right? So answer very quickly. Does it exist? Who thinks it exists? Wow, you were quick. How come you were so quick? It's sorted, right? Maybe that's what helped. Anyway, so should is in there. Could, is it in there? It's not. And the reason you could be so fast is, again, because it's sorted, because you know exactly that you're supposed to look like somewhere like here, right? Okay, so could is not. Now you need to locate it. And again, because it's kind of sorted, so the brain automatically goes there, probably with a binary search, right? That's how we do it automatically. We locate the posting list, and that's it, right? But this is something we did in our brain as humans, right? But of course, for a computer, we need a bit more to explain to the computer how to do that. So we have a missing part here on how we actually find the term that we are looking for. So for example, if we look for E, we need to find a way that we can efficiently find E. And by efficiently, I mean ideally O of 1. Logarithmic is fine too. Linear, maybe not, because you can have 500,000 terms in there, right? So probably linear is not good, but logarithmic or O of 1 is actually good, right? So we need a data structure for that. Now, the first solution that who knows what a hash table is? Almost all of you, right? So you saw that in the data structures and algorithms. So it's kind of a magic thing. So we have A, for example, that's a term. And we have this magic oracle, it's called a hash function, that gives us some integer. And in O of 1, we get the results, right? It has very nice properties, right? It's deterministic. It always returns the same results for the same input. If it's nicely implemented, so ideally there's no collision. So every value would give you a different hash. But of course, that's in theory, because in practice, you have collisions, right? But a very good hash function should at least try to spread it more or less evenly, and if it's a large number, to avoid collisions when you have a small number of terms to store, right? But anyway, this is going into cryptography considerations, right? So the notion of hash. So we have a hash that might give us 7, for example, excuse me, in the case of A. Again, it's instant. You call hash, bam, 7. What is there in hash? Well, typically it's going to do some bunch of addition, multiplication, modulo. The easiest implementations are like that. So this is why it's so fast. We get 7, and we do it just for all the terms, right? So now we have a hash table that has all the terms in there, and we can then extend that hash table with the actual postings list, right? So this is the same thing as we had here with the standard inverted index, right? Except that now it's organized with a hash table structure. And when you have a query that is incoming, you use the hash function that in O of 1 returns the position that you can use to look at. Then you do modulo 12 in that case, right? And there you go. And in O of 1, you have the results. Okay. What are the limitations of hash tables? What can it not do? On Zoom, maybe? No? Okay, then I'll tell you. So imagine that now you don't look for a specific term, but you look for a range of terms. And we'll see why later today. It's actually important to be able to look for a range. This is called the range query. Now, if we look for the range A to C, how do we do that? Well, it's not easy, right? Because this is just Tolerant. It's all mixed, and there is no easy way to just look at it. So the only way we could think of is to enumerate all the possibilities between A and C, right? So in that case, it's obvious that it's A, B, C because we just have letters. But in practice, you cannot do this. If you do it on words in a dictionary, and I tell you, give me all the words between information and retrieval, then that's not going to be easy, right, to construct the entire list. So you can't, right? It's really very, very difficult. So at best, you might be able to enumerate, then you do 3 lookups, but this is not ideal. For whom is that clear? Right? So hash indices are absolutely not meant for range queries. It's meant for what is called a point query, right? And by the way, these hash indices are exactly the same ones you have in a relational database, right? In a relational database, when you have what's called a point query, so it's select from where, and the where criterion is very precise, like an equality of a specific attribute. Then you have hash indices that return to you the results in O of 1. And exactly like here, if you have a query and in the where clause, you have a range, like the year must be between 1900 and 2000, then the hash index is not going to help either, right? Do you know what structure you have then to support range queries on Zoom? Awesome, then I'll tell you. This is exactly what's the lecture. Binary tree, yes, almost. So trees indeed. We'll see that binary trees work, and there's something even better than binary trees that's called B trees and B plus trees. I'll tell you everything about that. Who heard about B trees? B plus trees? Okay, then I explain everything to you. All right, so we have this limitation here. There is no support for range queries. In real life, the hash function might also not be perfect. So what happens if the hash function is not perfect is you are going to collide. Here we were lucky. There was exactly one term in every cell. In real life, that's not going to happen. It's likely there will be a collision, and maybe you're going to have, I don't know, A and D in the same cell here. If that happens, then you need to do something about it. And typically, the way you do that is that you enhance your hash table with an additional structure that allows for collisions. So you not only have the lookup of the hash, but within a cell, you might have multiple values, and you can have an additional linked list that iterates through the values, right? But it's extra effort, and it complicates the implementation. All right, so hash function is not perfect in real life. And on top of that, there are space requirements. If you want to avoid the collisions, then you need a lot of space to have room. Yes? AC, that would be 1, 2, 3, right? Yeah, absolutely. What speaks against it is that here it's possible because we have letters. Now imagine that instead of this, I give you a real standard inverted index with 500,000 terms. And I give you an interval with 2 words. This is going to be, this can be very costly. So first you might need an actual dictionary with an ordered list, and then you could potentially go through the words, right? But then it defeats the whole purpose of the hash index, right? Because then you're again going to go through the ordered list of terms and look them up here, right? So it's just inefficient. That's not a good. You could, right? But it's not a good way of doing that. All right. Okay. Never hesitate to ask questions, right? This is exactly what we are here for. Now, I'm going to jump in on the idea that was mentioned on Zoom, which is a great idea, which is the idea of a binary tree. It kind of makes sense because when I showed you the slide earlier with the ordered list of terms, it was all ordered by term, and you almost immediately answered. And again, in your brain, you probably did a binary search. This is what you do with a dictionary, a real dictionary, like this huge book, right? We typically learn that in primary school. If you look for a word, you open it in the middle, and then you see where you are, then you cut in two, you cut in two, you cut in two, and then at some point you find the word you're looking for, right? Of course, now we have the luxury of just typing in a computer and it appears instantly. But if we use a dictionary, a printed dictionary, then we basically use a binary search. And this is something we do very naturally. But if we want for a computer to do it, we need to guide the computer a little bit. And what we do is, in fact, that we materialize the binary search, right? We just materialize it in something that's called a binary tree, which is a starting point. That looks like this. So this is all in theoretical computer science. It can quickly get very complex because the number of ways you can build binary trees and binary search trees and so on, there are so many different kinds of trees that I'm not going to go, of course, into them. So on the very, very high level, in a binary tree, you have at most 2 children per nodes. It's ideally weight balanced. So if it has the property of being balanced, because then you could also not require the balance, right? But you can basically require that it's weight balanced, that it's more or less even on both sides. Like this, for example, that the difference can be at most 1. So you can accept 0 or 1 as a difference, but not 2. So for example, you could reject that on the grounds that this is imbalanced, right? Here, the weight is the total number of nodes here, 1, 2, 3, 4, 5, and here 1. So here, that's imbalanced because this is 4, and you only accept 0 or 1. So this is the sort of things you can do, right, in these structures. There are binary trees where you require that the number of children is exactly 2 or 1 or 2 and so on. So there's basically plenty of ways you can constrain them, right? But ideally, if you want a good index structure and you want a worst case, because if you look at the depth of the tree, that's basically your worst case in terms of lookup, right? So you want the worst case to be acceptable. So this is why you would like your tree to be more or less balanced, right? So here, the worst case is 1, 2, 3 comparisons, right? 1 comparison here, 1 at that level, 1 at that level, so that's 3 comparisons. Here you would have a worst case of 1, 2, 3, 4 comparisons. For whom is that clear? All right. So this is the first idea that you could use a binary tree in this way. So it's an art of programming, basically, to build that. So as soon as you have an imbalance, you automatically rebalance. So basically, this is if you keep updating the tree as new terms arrive, and then you get imbalanced, then you have algorithms that basically put it back into balance, right? Now there are a few, so among all the properties you can have in this kind of trees, let's put integers in there, then we'll have terms actually on the nodes, but let's put integer to start with. Some of the properties that you might require in a binary tree, I think then is a binary search tree, is that when you have an integer in there, like 4, for example, in the roots, then you require additionally that everything on the left must be less than 4 and everything on the right must be more than 4, right? So this is one additional property that you could require. If you have that property, the reason it's called binary search tree is that then you can very easily look things up, right? Because then you just compare what you're looking for with the current node, here 4. If it's less than that, you go to the left, and you just continue comparing all the way. And this is going to take what complexity in the number of terms? Answer A, O of 1. Answer 2, logarithmic. Answer 3, linear. Answer 4, exponential. Yes? Sorry, answer? Logarithmic, yes, exactly, logarithmic, absolutely. So this takes logarithmic time. So you see, for example, in that case, you have 7 nodes, roughly 8, and it takes 2 lookups. So that's roughly plus minus 1, the logarithm of the number of terms. Yeah, perfect answer, logarithmic. All right, so this is the deal, right? If you have this property of the tree and everything on the left is smaller, everything on the right is greater, then you can use it in order to search things and look things up in logarithmic time. So of course, it's not as good as the hash table, right? In the hash table, we have O of 1, right? And here we are logarithmic. But you know, logarithmic is still fine. I mean, in terms of data scales, we are totally fine with that, right? Linear, so of course, generally in computer science, if you do software engineering, you basically learn that exponential is not good and polynomial is good, right? But if you do something at large scales, even polynomial is not good enough. Even linear is not good enough. What you want to do is to accelerate things is to go to logarithmic. Linear is still good enough if you scan through, like you do a whole aggregation of an entire database, then that's going to be linear, right? But basically, as soon as you go more than linear at large scales, this is something you don't really like so much. All right, so logarithmic, we actually like that in terms of complexity. Okay, so now I'm replacing the integers with terms because obviously what we want to index here are the actual terms. And so here we do have this property, but using the alphabet, right? That everything on the left of oath comes before in the dictionary, right? Starts with C, B, N, comes before O, and on the right, P, O, T, that those come after, right? O, A, O, R, so this is later, right? So yeah, we have exactly the same property here with the terms. Now, let me give you one more bells and whistles that we can have in there. You notice here that all the nodes are in the same color. They're all yellow, light yellow. So we basically distribute the terms that we have. So these are basically the terms on the left of our standard inverted index, right? Now we distributed the terms all over the tree. Some of them are on the leaves, some of them are on the middle, one of them is on the root and so on. So we distribute them all over the place. Now, what we do is we connect each one of these terms with the corresponding postings list, right? So auth is going to point to the list of document IDs corresponding to that term, can as well, and so on. So now let me rotate the thing by 90 degrees like this. And now you should have an aha moment, right? This is where it connects, right? We now have the standard inverted index, but now we have this tree that organizes the nodes. And now you see, unlike the hash table, this is sorted, right? You could do a traversal of the whole tree. You have the algorithms for that you saw in data structures and algorithm. There is a linear way of traversing the tree to list the terms in alphabetical order. And this is why range queries are actually supported, right? Okay, who is following? Okay, very good. We are almost reaching the break. But what's nice here is you see, we are adding the pieces of the puzzle with things you already know from other lectures, right? So when when you start visiting these fundamental lectures, like, I don't know, linear algebra, analysis, data structures, algorithms, and so on, at first, it might feel like, why am I learning all of that? But then the real good feeling is when you start actually seeing that used all over the place. Linear algebra, probably when you start doing machine learning, that starts actually making sense, right? Or even quantum physics, quantum computing. All these data structures, the notion, for example, the notion of tree, the notion of map, and so on, all of that is everywhere, all over the place in database lectures, right? And now you see for indices, it's actually to retrieve data that we like to have these hash tables and these binary search trees and so on and so on. So this is a direct application. Do we have a question in the Zoom chat, or is it from earlier? Mm-hmm. Okay. All right, now let me change something just to show you there's 2 ways of doing that just before the break. Yeah, let me tell you just before the break. In that case, we spread the terms on all the nodes, right? Everywhere. There is also the alternate design where we only put them on the leaves, right? So the terms will only be in here on the leaves. And what there is on the nodes here doesn't have any postings list. The only purpose of them is for the comparisons. to look up when you go down the tree and find this, but you only have the terms here at the leaves with the posting list. This is the alternate design, right? Like this or like this. Do we have a question on Zoom?
So the question is, are the recordings uploaded somewhere?
Yes, it's all on YouTube. So there is, you can find them. So on the Moodle, normally we put them every week. If you don't want to wait to be in the Moodle, you can directly go to the YouTube channel, right? All of my lectures are there, and you will see them immediately if you go there, right? So it's all on YouTube, okay? But we also try to put the link in the Moodle so that you can also view them here, right? All right. So I think this is time for the break, well-deserved break, and then we'll continue, and then I'll move on to B trees and B plus trees after the break. So see you in 15 minutes. Thank you very much.